Okay, so we have a lecture on the goodness of fit test. This is often called chi-square goodness of fit test because the variable, the test value will be a chi-square random variable. Okay, this test is used when you are expecting something to happen in a particular way, some kind of distribution to happen, and then that what happens might be or might not be what you expected. So then you are testing whether that what you expected actually happened, or that of course what you expect and what happens will always be slightly different, right? Because you don't necessarily going to have things exactly fall into place as you they're supposed to. For example, if you have a population in which you have 51% female and 49% male, if you select at random 100 people, it might not be 51% female and 49% or 49 males and 51 female. It might be different. It might be slightly different. But that small difference will not matter. It will not be of statistical significance. But for example, if it happens that you get 80 male and 20 females or vice versa, then obviously something is wrong, right? Either with the way you are selecting or with the population that you expected one way, but it happened completely different, in a different manner. So that's the story about this test. So let me give you one example so you can see better what it is. So you're playing with a gambler who uses a pair of dice. So what you expect to happen is one thing, but what actually happened is another thing. So for example, he made 100 rolls. So you have the number of rolls, and then you have the count of sixes in those rolls. So it could be, since there are two dice, right? It could be that you don't have any sixes. So you have no sixes. And it could be that you could get one of the dice 6 and the other one not. It could be that you get both dice to be 6. So you can have either 1 or 0 or none on the top of a die. Excuse me, 1, 2 or none, right? The 0 is both dice or something else, like a 3 and 4. One die is 6 and the other one is something else, like maybe 3. And then you have a 2 when you have both dice. You have a 6 and 6 on each die. You have a 6. So you're playing with this guy, and he somehow get 52 times nothing. Meaning you get something that is not 6 on either of the die. Then he's got the 42 times with one die showing 6. Okay? And then he also had 6 times both dice showing 6. So maybe he's playing the way that he's betting on sixes, right? So the question for you is, all of a sudden you start losing money. The question for you is this fair game? Okay, what would be a fair game? Well, it would be relative to the distribution of fair dice. So we know the distribution of fair dice would be, you can have 36 different outcomes. You can have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. That's 6 already. Then you can have on the first die 2, and 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Meaning the second number is the second die, right? Then the first die could be 3, and the second die could be 1, 2, 3, 4, 5, 6. The first die could be 4, and the second die could be 1, 2, 3, 4, 5, and 6. the first die could be 5, and the second die could be 1, 2, 3, 4, 5, 6, and the first die could be 6, and the second die could be 1, 2, 3, 4, 5, or 6. In other words, you had something like this. So this is the code what can happen. So you have the first die 1, the second die 3. And all of the sorts of different things that can happen. They're all equally likely. So 3, 1, 3 on the first die and 1 on the second die is equally likely as any of the other of the outcomes you can have here. So this is the thing that would be possible to happen. And they're all equal, again, they're all equally likely. I believe you studied this in the statistics 1 or 3, right? I hope you did. Okay, so as you can see here, these are all possibilities that you could possibly have. Okay? So, this is actual. You're playing the game and this is actual what happens. Now this is expected. What should you expect to happen? So you have 100 rolls in total. Okay? So if you roll 100 rolls in total, take a look at what you have here. This part here doesn't have any sixes. All of the sixes are here at the edge. So you have 5 times 5, 25 different outcomes out of 36. 25 out of 36 different outcomes that are without any 6. Okay? That would be approximately 69%, 69.44%. Okay? Out of 100 rolls. You should have 69.44 rolls to be without any 6. Okay? Because again, this is 25 out of 36. That's your chance of getting something that has no 6s. And that is approximately 69.44%. Now out of 100 rolls, that should be 69.44 rolls with no 6s. Yeah, I know. You can say, well, it could be 69 or it could be 70. How can that be 69.44? We're not talking about here what actually can happen. We're talking about the expected number. An expected value is not necessarily going to be the number of roll. It's expected value, right? You remember that from the story in 1 or 3. The expected value is not the actual value. Okay, now let's take a look how many times you have 1 6. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, right? This is with 2 6s, so 10 out of 36 times. There's a chance of getting 1 6. 10 out of 36 times, and that would be 27.78%. That's 27.78%. So this is the chance of getting 1 6. So out of 100 rolls, this many should be with 1 6. Okay? And again, how many times you have 2 6s here? Once. Out of 36 different outcomes, there's only one way to get both sixes. 1 out of 36, if you do this calculation, should be 2.78%. So out of 100 rolls, you should have 2.78%, 2.78 rolls that are with 2 sixes. That's expected. Okay? So again, this is what actually happened. This is also 100, right? And this is what it should happen. Okay? This is what it should happen if the dice are fair, and this is what actually happened. So, there is a difference. Okay? What is the difference here? Well, I should have less than 3 times both sixes. But he has 6 times 2 sixes. I should have 28 times maximum 1 6. He's got 42 times. And I should have like 69 times no sixes at all. He's only have 52 times no sixes. So yeah, this is a significant difference. What you see here, he's got sixes more often than what you should have. Now the question is this cheating? Because if he's getting money out of this, and if he's playing and betting on sixes, he does have more sixes in the game than he should be getting. So now the question is this a significant evidence, significant statistical evidence that there's a cheating here? Okay? Now we're going to say how you're going to find it out. Okay? We have a Pearson theorem. Carl Pearson again, the statistician that we mentioned before. According to his theorem, if you subtract actual minus the expected value, and you square that, and you divide it with expected value, and sum that all, for every category, you will get it should be, if it's actually distributed by the expected, it should be the chi-square random variable. So in our story, that should be actual minus expected. 52 minus 69.44. You square that, you divide it with 69.44. So again, actual minus expected, squared, divided with expected. That's one category. This is when you have no sixes. Plus actual 42 minus 27.78, square that, divided with expected. That's a second category, the same calculation. The actual minus expected, square it, divide with the number of expected. And the last one, I have 6 minus 2.78, square that, and divide with 2.78. Okay? So you have 3 terms. The first category, no sixes. The second category, 1 6. The third category, 2 sixes. And sum it up. Now this is not too hard to calculate, but I'm of course not going to be calculating that now. I already did that. So I get the value which is 15.39. You check it out. Okay? What Carl Pearson theorem says, and we're not going to prove that theorem, but what he says, if this behaves like what is expected, if it behaves like what is expected, there might be slight difference, because something that is expected will not going to happen. By the way, of course, it can happen because you have the decimals here, right? There will be slight difference, but that difference could be a lot more, and then it's going to be a suspect, or it could be just a little different. But one way or the other, what we have here is a plenty of difference, right? You can see here, you can see here, and you can see here. Just in my visual, I can see that there's too much of a difference here, or a lot of difference. Okay, but again, if this is guided by what it should be, then we would get chi-square random variable. With how many degrees of freedom? Because chi-square random variables always have degrees of freedom. So what degrees of freedom are? How many categories you have here? 3 minus 1, 2. Chi-square random variable with 2 degrees of freedom. So Karl-Pearson theorem says that this must be a chi-square random value with 2 degrees of freedom. Okay? And now you have your test. Right? So I'm gonna say that this thing here, so how I calculate it, this is how it's calculated. So it's a very simple formula. The formula is sum observed or actual, this is sometimes called actual or observed. Right? What actually happened, or what is observed that happened. Right? So observed minus expected. You always have to know what you expect, right? Square that, divide it with expected, and then sum by every category you have. So this is the chi-square random variable with 2 degrees of freedom in our case. Okay? And in our story, that's 15.39. Okay? Now I know how the chi-square random variable look like. The chi-square random variable look like asymmetric curve that starts at 0 and then it has a prolonged tail into the right side further away from 0. Okay, something like this. Okay, you don't have to be careful in terms of whether this is going to be really precisely a chi-square random variable. It just looks something like that. The hump starts on the left side, and then you have a pronounced tail on the right side. What are we testing? Okay, set up for our test. I'm going to have to pull this a little bit off so I can write. We have H0 hypothesis. Now this is a verbal hypothesis. We don't have any numbers here to talk about. In our story, the dice are fair. There's no cheating in the game. So what happened? It's going to be slightly different than what it should have happened, but it's not big difference. Okay, so the dice are fair. Alternative hypothesis: the dice are not fair. There's a cheating in the game. You can say also, what has happened is what is expected. What has happened is what is not expected. And then you have the test value. This is going to be the test value. You can also call it test statistics, right? It's a test statistics. Test value, test statistics. And now you have a rejection criterion. Rejection criterion, you have the tail. Do you have this value in the tail? So now the question for you is, what is the level of significance that you want? And what tail we are talking about? So we're going to use a level of significance when you don't have any better idea, right? We're going to use the 5%. Okay, now you're going to have to remember that, because we're going to use that for any further chi-square test that is going to be based on the Pearson theorem, which is, we're going to use another one. This is only right tail test. There is no left tail test, there's no two tail test, this is only right tail test. Why is that? I'm going to explain it in a moment. But it's only right tail test. Okay? So when you're talking about level of significance of 5%, you're talking about this area here, that should be 5%. Okay? And this is a chi-square on the variable, chi-square on the variable with 2 degrees of freedom. Again, 2, 3, 3 categories, 2 degrees of freedom. So 1 less than the number of categories. Okay? So you need to find this value. So you're going to open the tables, the chi-square tables that you have in the on the blackboard or in the textbook, which if you have a textbook, you will find that in the textbook. And in that, you will be looking for the level of significance. The right tail is right on the top. It's going to be that alpha. And this time, no confusion at all. That alpha in the table is actually going to be the level of significance you're looking for. So you're going to be looking for 2 degrees of freedom and the 5% alpha in the chi-square table. Again, and the value I found I hope you can see. So I have 5.991, right? That's in the chi-square table. I hope you can see that. Right. One way or the other, you can take a look at the table. It's not really that hard to find. So alpha on the top of the table is 0.05, and the 2 degrees of freedom, and you're gonna be able to see the number is 5.991. So this critical value here is 5.991. Now take a look at the test value. The test value is deep in the tail here, right? Somewhere, I put them at random. Of course, this is 5. There's another 5. There's another 5. So it'll be somewhere there, further away. What does that mean? Just like in every test we did before, that means that you have a rejection on a null hypothesis. The dice are not fair. That's acceptance of the alternative hypothesis. The dice are not fair. The guy is cheating. What has happened here is statistically significantly different. There's a significant statistical difference than what should have happened. It should have happened that you get the chi-square on the variable should be here, right? Where the hump is, where the most probability is. But it's not. It's somewhere there in the sliver of the tail. That is unusual, okay? And it's statistically very much different than what should happen. Okay, so we will say, okay, there is at least 95% chance that he's cheating, and probably a lot more than that, because it's much further away. Even if I use 1%, I would get him on cheating. If I use 1% and you look at the table, and 1% would be, the critical value would be 9.210, 1%. So even at 1% significance, I would say that he's cheating, because 15 is more than 9 point something. So I'll be able to say that he's cheating with at least 99% certainty. I am at least 99% sure that he's cheating. So that's the story of this example. Now let me give you another example. So let's say you're making a poll. So in your poll, I used to do it in the past. In your poll, you're gonna have some students that are doing survey for you. They're doing polling for you. And so when they are doing polling, you want them to poll the population in a way is representative of that population, so that you can get the idea what's going on in the population, because you're not really looking for what's happening in the sample. The sample is selected so that you can get an idea about a population. Okay, so what we have is some sort of a political poll. So you have that I'm interested in what is the opinion of the people that are voting. I can look at it in two, three, maybe four different ways. One way certainly is going to be by the age groups, because I know that the older people are voting more often than the younger people. So I'm not going to be looking for the polling that is going to be randomly selecting older young people. I'm going to be looking for the polling that's going to be selecting the people in the way that how often they vote. So I know that in the age group between 18 to 29, 12% of the voting population is in that age group. Likely voters. The people that are likely vote are going to be 12% in that age group. So only all of the voters you have, of the voters are in this age group between 18 to 29. In the age group between 30 and 39, we have 15% of the voters. Now the next age group is going to be 40 to 49. In this age group, 17% of the voters are in that age group. And then you have two more age groups, 50 to 59 and above 60. So in this age group we have 44% of the voters, and in the age group of 60 plus seniors, most disciplined voting population, almost half of the voters are in that age group. Almost half of the voters are in this age group. So that's why they matter the most, right? Because they vote the most. So if you are a politician, you want to make sure that you get your acceptance in these two age groups. This group, more or less, right? 12%. Young people don't vote. We know that. Okay, well, they do, but small numbers. Okay, so I got these students of mine, and I give them the job. They want to collect the opinions of people of whatever that subject was. I'm not really particularly interested in talking about it now, but I was asking them to collect the opinion of the voters. So this is what I got. They get me the poll. But the way I get from them, even though I guided them, so I said, you need to have this many older people, you need to have this many people from the age group of 18 to 29, this many from 30 to 39. But one way or the other, they really didn't get me that what I really wanted. They give me slightly different stuff. So in the age group of 18 to 29, out of whatever collecting, I got 38 people. In the group between 30 to 39, they get me 31 respondents, so those are the people that are polling. In the 40 to 49 group, they get me 39 people. And in the last two group, I got, looks like I made a mistake here. This is 21 and 25. Yeah, this is a lot more than 100%, right? So it's a mistake. Excuse me. I was just copying from the table, but I copied it wrong. So, yeah, this should be 5 plus 1, 6 plus 7, 13 plus 7, 20. To carry on, I have a 7 here, 8, 9, 10. Yeah, sorry. So I get the two more age groups from my poll. This is what I got from my students. So this is the actual, and this is what I expected. What I expected to get. So I wanted to get this distribution. And here, of course, I have 200 people here, right? 200. So you add those numbers here. They give me a sample of 200 people. They collected a sample of 200 people. Okay? So now, so this is the actual thing I got. Okay? And if I was looking for 200 people in the poll, and I wanted to have that to resemble the voting population, I expected to get 12% out of 200 is 24. 15% out of 200 is 30. 17% out of 200 would be 34. 21% out of 200 would be 42. And 35% out of 200 would be 70. Right? So this is what I expected to get, but this is what I got. Right? So again, let me repeat this one more time. I know that in the voting population, the people that are voting, I have 12% of those are in the age group of 18 to 29. So if I have a sample of 200, and if this sample should resemble to the likely voters, then I need to get 24 people in that sample from that age group. If I have my voters, my likely voters, from the age group of 60%, 60 years or older, there will be 35% of the voters in that age group. So when you're looking at the people that are actually voting, 35% of those that are voting would be in the age group of 60 or older. So which means if I have a sample of 200, I should have 70 of them. 30% out of 200 is 70. So I should have a 70 in my sample. So this is what I should get, but this is what I do have. So my students were collecting the sample and some kind of political opinion, but this is what I have in the sample. You can see what I have, that this is not anymore percentage, it's actually the number of people in the sample. So I should put that in number of voters in the sample. And again, this is also not percentage out of 200, this is now the number that I expected to get. So again, I'm talking about the number that I expected to get and the number that I get. So my students give me too many people in the age of 18 to 29. Not a surprise there, right? Because they were looking for their, how do I collect the poll? I go over the people I know. And the people I know are all younger because I'm young, right? A student. So that's what I got. 38 versus 24 I expected. Now, the second group, 31 versus 30, that looks pretty good. It's almost there. 39 versus 34, that is not so bad. 44 versus 42, that looks great too. But then I have here, they were not getting too many old people. For whatever reason. They get only 48, and I was expecting to get 70. That's a big difference. So now I have this problem, that I get too many young people and too little old people. Is this just random case, or is it something that I can say, hey Fox, you gave me this poll that you collected, but this is worthless poll because in this poll that you collected, I don't have this to be representative of the likely voters. This is what the likely voters should look. If you have 200 likely voters, you should have 24 from this age group, 30 from this age group, 34 from this age group, 42 from this age group, and 70 from this age group. But you don't have that. You give me this, which is very different, and I have too many young people and too little old people. Okay? So I'm kind of having a problem here. Now you can say, is this really all that much of a statistically significant problem, or is it just maybe it's your opinion that you have a big problem here? Can you use this poll? Okay. Hypothesis 0. In the hypothesis 0, I would assume that this is good. The poll age distribution is as expected. I don't want to write everything, but you can continue. You can write the age distribution you have in the poll is okay, is as you expect. The alternative, so this is verbal. The age distribution is faulty. Is not representative of likely voters. I should write here, the age distribution is representative of likely voters, so my poll is okay. The age distribution is not representative of the likely voters. Likely voters is the people that actually do vote, or they're expected to vote, right? So in the last, this is how they look like. 12% in this age group, 15% in this age group, 17% in this age group, 21% in this age group, 35% in this age group. I'm talking about percentage, right? But out of 200, you double everything. Okay, so now you have a test value. And test value is that Karp-Pearson test value, which is the actual, when is the expected, squared, the observed, or the actual, minus the expected squared, divided with expected. So you need to write 38 minus 24 divided with 24, you have to square the numerator, plus the second age group, 31 minus 30, I could just write immediately 1 divided with 30, square that. The next one is 39 minus 34, that's 5, right? Divided with 34. The next one is 2 more to go. The next one is 40 minus 42, which is 2. Divided with 42, the top must be squared. And the last one is 48 minus 70, that's going to be a big number. I have to square that, and I have to divide it with 70, and I have to add it now. And all of that is a pretty lengthy calculation, but I got 15.94. So all of that is approximately 15.94. Okay, that's my test value. I don't have enough space, so I'm going to erase the actual here, because I need a rejection criterion here. Rejection criterion will be chi-square random variable. So now I'm doing something again, approximately. how many degrees of freedom? Let's see, 1, 2, 3, 4, 5, 4 degrees of freedom. So this is a chi-square under variable 4 degrees of freedom. What am I going to use? I am going to use, don't have any better idea, 5% again. 5% level of significance. So this is my right tail of 5. And I need to look again in the chi-square table, so I'm not going to try to show you that. It's not really that hard to find. Pull out the chi-square table. Look at the top when you have the right tail of 5%. Look at the 4 degrees of freedom in the chi-square table. And it will not take you long to find that the number you're looking for, the critical value, is 9.488. So that's this value here. Okay? Look at your test value. Test value is here, somewhere in the tail. And one more time, you have rejection of the null hypothesis. So null hypothesis is verbal. So this test here has a verbal null hypothesis and verbal alternative hypothesis. So the null hypothesis says age distribution is as I expected according to the likely water distribution. The alternative hypothesis is that age distribution in my pole is not good. It does not reflect the age distribution in the likely waters. Okay? I just rejected H0, so conclusion is that I can throw that pole into garbage. What I get out of that pole is not useful to me because it does not give me the opinion of the likely waters. It gives me the opinion of the group of waters that are more young than old. I mean, there are too young and there are not enough old people there. There are two age groups here that have big problem. So you look at those terms here, this problem here. This term here and this term here. They are contributing the most to that 15.94. The other three terms in the middle are not that much of a problem. This one is almost nothing. This one is not a big deal. This one is a little more, but not much. This one is the one that makes problem, and this one is the one that makes problems. So when you add those two numbers, that most of the 15.94 is in here and here. So this is where I have a problem. I have too many young people and I have too little old people. So that's my problem, and I just rejected the null hypothesis, so I can say the pole is not good. I can't really use the conclusions of the pole because it doesn't resemble what I was polling from. It doesn't resemble what I wanted. I wanted to have a likely waters opinion, and I don't have a likely waters opinion. I have opinion of younger people, okay, which is not something I wanted. Okay. Let's do one more example. Another example from the lecture. Okay, a college. So in the college, when you have a community college, you want the community college to resemble community, right? Because that's the point of having a community college in a community, to have student distribution similar to the distribution in the community. What am I talking about? I'm not talking about the age, of course. The old people are not going to go study to community college. But I'm talking about the race, probably, or the income level, things like that. That income level is usually not expected either, because the people that have a lot of money, they're not going to go to community college. They're probably going to select some elite college if they can enter to that college. But the race, I'm interested in race to be distributed as in community. So I'm having here some particular college in which I have, you can select the number of races that you want to use. I have 2,341 to be white. Okay? Then I have a second race I'm going to use is African American, right? And in the college we have 702 of those. Then I'm going to probably use the Hispanic population, right? And the Hispanic population we have 1,016. I'm not talking about our college. I'm talking about some other college. I just actually made it up, to be honest. But that's something like that, all right? And then we have. You could talk about more races. You can select Asian and Pacific Islander or whatever that is used, but we're just gonna say others. So there is another group of people that could be everything else, and even some people that don't want to declare the race. So, and we have 551 of those. Okay, so this is what we have in the college. So this is actual. Or you can say observe. Okay, now what you want, what should happen, is what is distribution in the community. Okay, so you expect distribution as in community, in the community. So you have to have some kind of demographic survey or some census or something to know what is going on in the community, how many you have in the community from each of those races, and in the community we have 1, 2, 3, 4. 1, 2, 3, 4. Out of the white population, we have 49%. Out of the African American population in the community, we have 15%. 15% of the people in the community are African Americans. Hispanics, there are 23% Hispanics. Ooh, excuse me, wrong place. And the others in the community are 13% of the others. All right. So now, do we have the population in the community college reflective of the population in the community? Now this is hard to compare because this is a number and this is the percentage. So basically what you need to really do is to calculate the expected based on the numbers now. So the total here is 4,610. You can add this up, right? That's your total here. 1, 2, 3, 4. Add it up. 4,610 people in a community college. Out of those, 2,341 are white, 702 are African Americans, Hispanics are 1,016, and everybody else is 551. Okay, now you do need to get here also 4,610. And what should you expect? 49% of 4,610. So I gotta multiply that to find that number that is expected number. And I come up with 2,258.9. So now this is not percentage. It's the number of individual that you should expect to have in the college. Again, the expected number is not the actual number. So you're not gonna, of course, you're not gonna have 2,258.9 people. You're gonna either have 2,258 or 2,259. But this is expected number. So the expected number is not the actual number. So you should not expect to get the rounded number. Now I had to have 15% 15% of African Americans, so there will be 15% of the 4,610. So again, multiply this number with 0.15, and you end up here with the, I got 691.5. Okay, the next one, Hispanics, 23% times 4610. You ended up here with 1060.3. And everybody else, 13%. And so now you got the expected number that you should have in the college, which is 599.3. Okay, so I can compare these two tables. This is a little bit undercounted here. I mean, overcounted here. More whites than you would expect. African Americans are not that far away from this number, so looks like okay. Hispanics, okay. So you have somewhat less than what you would expecting. Okay, 44 less. And now these others are also less than what you're expecting. You're expecting that number over there, and you have this number here, so it's like 48 less what you expected. Now, it's not that much of a difference, so you know, if you're just an administrator, you can say, no, it looks pretty good. And we don't have, you know, there's nothing particularly going on strange here that, you know, sometimes you go into some of the southern states and you can find a university when you're in an environment you have 30% of African Americans, and in university you're going to find 3 or 4% of them. So that something's going on, some kind of segregation problem they have in the school, right? So this doesn't look like that. It looks like, you know, the numbers are not exactly the same. You shouldn't expect that. Is it statistically different? Statistically significant? Is this difference statistically significant? That's the question. So now you do the test. So I'm gonna need H0, race distribution in the college, is as in the community. Which it would make you happy as an administrator, right? H1 race distribution is not representative of community. Which is a problem. You're a community college, you should be representative of the community, but you're not representative of the community. So that's a bit of a problem, right? So then you have to do some kind of activism in the community. You have to promote, in the parts of the community you don't have enough, you need to promote your college. You need to get some work on that, right? This is what is always done. Every college does that work. They go into the community, they promote themselves and so on. But you really need to target a particular group depending what group is lacking, and so you're going to find it out now. Test value. Okay, now the test value is the story that we have. So this number minus this number squared divided with this number, so we have the actual or the observed minus the expected, square that, divide with expected, plus second number 702 minus that one over that, 691.5, square that, divided with 691.5. The next number 1016 minus 1060.3, square that, divided with 1060.3 plus, and the last number 551 minus 599.3. We got 0.3 and 0.3. Yeah, okay. Divided with 599.3. Okay, lengthy calculation, right? And that is, I got this number calculated somehow. I got 8.8869. That's a test value. Since I calculated that now, 1, 2, 3, 4 categories, chi-square, instance of a chi-square random variable with 3 degrees of freedom. Rejection criterion. Is it in the tail? Again, you gotta remember the chi-square random variable looks like something like that. It's not precise. The hump starts in the beginning and then you have pronounced tail to the right. The more degrees of freedom there are, the more it's going to resemble to the bell curve, but it's never a bell curve. It's always asymmetric. Okay, what am I going to use here? Well, don't have any better ideas. I'm going to use 5% again. You don't have to use 5% all the time. You can choose something else. I don't have any better idea. I'm going to use 5% again. So this is a customary thing. When you don't have any better idea, 5% is a usual thing to use. But again, you're not required to use 5%. You can use anything you like. So now I'm looking for the 3 degrees of freedom, right tail only, chi-square test of goodness of fit is always the right tail. Okay, right tail and 5%, I find 7.815. Okay, where was my test value? The test value is in the tail. Oh, not good, right? So I'm rejecting null hypothesis again. What am I going to say here is, when I'm doing this analysis for the administrator in the college, I'm going to say, all right, we have a little bit of a problem here, because I am a 95% sure, at least 95% sure, the attendance of the college registration is not reflective of community. And I would probably say this is the biggest term here. I mean, 1, 2, 3, 4, you're also adding 4 numbers, you get 8.88. One of them is bigger than the other, so maybe 2 of them or 3 of them are bigger than the rest. This one is definitely bigger than the rest. You have a big difference here. So you have too many whites, and you don't have enough Hispanics. And even this group of others. And you're probably okay, this number is really small. This one is the smallest. You can say, you're okay with African Americans, but you have too many whites and too little Hispanics, or vice versa could happen, right? But that's what I see here. And this other group also, there are not enough of them either. So whatever they are, maybe you have, in the community, maybe you have a lot of Asians, and you don't have enough Asians in the college, for whatever reason. So you can set your administrator, you need to, it's not a big deal. I mean, this is a little bit in the tail, but you need to do some work here. You need to go and promote your college in this group of people, and on this group of people, whatever they are, because you don't have the race distribution in the college is not reflective of the race distribution in the community, for whatever reason. Okay? All right. So one more thing I need to say here. So I have 3 examples here. You can do the homework and do a lot more examples on your own. Why don't we have the left tail? Why is this test always right tail? Okay, let's think about it. Left tail is going to be here when you have very small values of the test value. So what's that about. If you have very small value here, that means that this is very small, this is very small, this is very small, this is very small, which means you don't have much of a difference. The chi-square test of goodness of fit, that will be a left tail, will be a test of how perfect your distribution is. And we are really not, right? When you say, "Ooh, this is really good." I mean, if you get the left tail test, you'd be really asking, well, do I get this really, really small numbers here, right? How perfect my distribution is. Is my distribution too perfect? That will be the question. And I'm not interested in those kind of questions. So this is not the thing you have an interest in. You're interested in whether your distribution is faulty, whether you have something that should not happen because you expected something else, right? That's why we don't have a left tail. So we only have a right tail test here. So this test, you got to remember that it's called often goodness of fit test. You'll find that on the calculator sometimes GOF test, and it's also called very often chi-square goodness of fit test, and it's based on the Karl Pearson theorem that says that this guy here, if the distribution, so you're hanging again the null hypothesis on its own rope, if the distribution is as expected, this should be chi-square random variable with 3 degrees of freedom. How many categories you have here? 4. 1 less 3 degrees of freedom. That's a Karl Pearson theorem. We will never prove this theorem. We're going to just leave it for graduate statistics. If any one of you ever get to the graduate study of statistics, you will meet this theorem. So Karl Pearson did that a long time ago, 100 years ago, more than 100 years ago. And we are using that. It's a very important test. Okay? So I'm done with this story. I want you to do the homework here. The homework on this chi-square goodness of fit test is the extra credit homework, which means if you do this homework, you're going to have whatever you do in that homework is going to be counted as an extra credit for you. So you're going to have more points. So I hope I made this make more sense out of that. So again, this is the test that you have a couple of things to notice. Number one is, of course, chi-square distribution. So it's asymmetric distribution. Number two, it's always a right tail test. Number three, that's different than anything we did so far, is that H0 setup of the test, H0 and H1, the null alternative hypotheses are verbal. They're not, something is equal to some other thing or something is not equal, something is bigger. No, they are actually verbal. So the race distribution in the college is representative of the community, race distribution in college is not representative of the community. And they're, by the way, conflicting, right? This is truly a statement, and this is exactly the negation of this statement. So there's nothing like left and right, it's just simply negation of this statement. They are in conflict with each other, they're inconsistent. Yeah. Okay, so you are going to hopefully do the homeworks to get this better idea on that, and read the lecture too. It's on the blackboard with those 3 examples written down piece by piece. And I also have, I think in the appendix, I did the simple case of when you have only 2 categories. Why would that be chi-squared with 1 degree of freedom? So basically in the appendix you have the Pearson theorem, but only in the case with 2 categories are in the game. So it's not in a full-blown Pearson theorem, it's just a little bit the light version of a Pearson theorem. The full-blown Pearson theorem, you can even find a textbook that some people were proving that theorem in 60 different ways, which is very interesting. So it's a very important theorem, but apparently Karl Pearson probably noticed that, and he proved that in one way. But some people went over and were proving that all possible different ways. So it's a scientific fact. So we are relying on that. We're going to meet it one more time. The Karl Pearson theorem on chi-square distribution we're going to meet one more time. Okay, I'm gonna end the story, and you do the homework yourself. Is everything okay?